Okay, so we continue with Shannon's theory, and so in the last class what we have seen essentially is what is the definition of perfectly secured ciphers, and we have proved certain results based on our probabilistic theories. Okay, so we will start with an example of perfectly secured cipher. So in last day's class we had seen an example of shift cipher. Okay, and the way the shift cipher was used is something which is commonly called as the one time pad. Okay, so one time pad is probably the only known mechanism through which actually you can conceive or think of a perfectly secured cipher. Okay, so what is the idea? The idea is as follows. It says that the encryption is very simple. You just take a plain text and you XOR that with any key and obtain the value of the ciphertext. Okay, so which means that your plain text essentially comprises of some letters like H, E, I and so on. So you see that all of this you can actually denote by some letters, right? Your plain text you can denote by some binary digits. Okay, and you consider that suppose your key also is essentially some binary digits. Okay, so therefore what you do is to obtain the ciphertext is just XOR your plain text and the key and obtain the value of the ciphertext. So the idea is that for every symbol you use, okay, your key is again chosen at random. So we have seen that, right? So if you're, so for example, if you use or rather consider a case where you have got an n-bit plain text, okay, and if you're transforming that into an n-bit ciphertext, then how many how many keys are possible? That key size is also n bits, right? So therefore there are total number of key possibilities are 2 power of n. So every key that you choose, if you choose at random, which means that we choose with a probability of 1 by 2 power n, then the ciphertext which you obtain correspondingly is perfectly secure. Okay, so the proof is also exactly the same as we have seen in the previous class. Okay, so you see, for example, that suppose a wrong key is used to decrypt, then what you do is that you take a ciphertext, you obtain a value of the key and you correspondingly XOR and you obtain a plain text and you obtain a value of the ciphertext. Okay, so if this was a wrong key, then it really does not make any sense, right? Some jumbled letters. Okay, so in this case you obtain a, you see that this is the actual value of the correct key and therefore you decrypt that. So this is just in order to show you what is meant by a one time pad. Okay, although I am not going into all these what is meant by the plain text and correspondingly what is meant by the ciphertext. This is just an example of how a one time pad works. Okay, so what we have seen is that for a given ciphertext of the same size as the plain text, there is an equiprobable key that produces it, and then we say that the scheme is unconditionally secured or perfectly secured. Okay, so therefore I hope we understand what is the meaning of one time pad. The one time pad, again I would like to repeat, is the only example of a perfectly secured cipher. Okay, but what are the problems? The problems is that although it is perfectly secured, it is actually impractical. Why? Because your size of the key, if it is the same as that of the plain text or the ciphertext, then you can use as well as any other mechanism through which you are sending the key securely to send the plain text also, right? Which means that you have got a secured channel, then why don't you use it to send the plain text as well? Why do you require encryption at all? Okay, so it means that it is not very practical. So in practical scenarios, what we would have liked? We would have liked to keep the key constant for various symbols, right? So which means that your cardinality of your set key A is actually would have been lesser than the size of the cardinality of C, right? But then that is practical and then it is no more perfectly secure. So which means that given any unbounded adversary or given any unbounded computational power, then you can always employ some techniques to break the cipher, to ascertain the value of the key. Okay, so we will try to understand such type of, so there is a discrepancy between the practical world and what you obtain in the perfect world, right? So you see some practical problems could be as follows, like the large quantities of random keys are necessary. Creating random is actually hard because we really do not know what is a random, how to create random stuff, right? So therefore it increases the problem of key distribution because you have to distribute the key as well. I will come to this problem later on, which means that a sender and receiver has to establish a value of the key, right? And if that amount of number of keys is actually enormous, then you have to do a lot of key distribution techniques you have to engage. That is a burden over your normal communication. So as I have already told you that encryption is always an additional burden, right? So you have to do it efficiently as well. So thus we will continue to search for ciphers in our class where one key can be used to encrypt a large string of data. okay, and still provide something which we have already told you as computational security. So it is no more than perfect security, but it is a computational security, which means that in today's computational power, using today's computational power, we should be able to prove that we are unable to break that system. Okay. So for example, if I just talk about DES, which is a data encryption standard, it uses a 56-bit key, and okay, and it's quite secured. Quite secured means in a sense of computational security. But if an adversary has power of 2 power 56 trials, then anybody can break it, right? So actually today people can break it. People can break it using today's computational power, using large parallel computers and things like that, large number of clusters of computers. People can break it in maybe less than a day. Okay. So therefore DES is no more computationally secured in today's world, and therefore we have to look for other standards. AES is another standard. Okay. But this is actually a good cipher, so we will discuss about DES also in our class. Okay, and because it's good to learn with DES essentially. So the summary of one-time pad is as follows. It was actually perfectly secured. Okay, I mean provably secured in the sense of perfectness when used correctly. So when used correctly means what? Means that the key has to be randomly chosen for every corresponding encryption. Okay, so ciphertext provides no information about the plain text. That is because why? Because your a posteriori probability of the plain text matches with the a priori probability of the plain text, right? So all plain texts are equally likely. The pad must be random, that is used only once, okay, and pad is known only by the sender and the receiver. The pad is the same size as that of the message, and there is no assurance of message integrity, okay, but I'll come to that later on. So message integrity, we have got no assurance, because in a one-time pad, even if you do not know the value of the key, you can actually tamper with the value of the message. Because consider a scenario like this. Hope this works. So suppose you have got M, XORed with the value of K, right? So this is the value of your ciphertext, that is C equal to M XOR K. Okay. So what does it mean? It means that we have got a corresponding plain text and you have a corresponding value of the K, right? That is the key. So this is the basic equation of a one-time pad. Okay. So now when we are considering about, or rather concerned about message integrity, imagine suppose there is an Alice and a Bob who are communicating among each other, and Alice sends to Bob this ciphertext C. Okay. And there is some other eavesdropper E who does not know what is the value of the corresponding key. Okay. But what he does is that although he knows that this is since he knows that this is an XOR of the message M and the key, okay, suppose what he does is that he just doesn't do anything but XORs this value with some other value of, say, some other random number, and transforms this C dash, makes it C dash, and sends it to B. Okay. So when B encrypts, or rather B decrypts, what does B decrypt and obtain back? B decrypts and obtains back M XOR R. No. So B obtains C dash and XORs that with the value of K, and he obtains back M XOR R, right? So suppose M was equal to, suppose he wanted to transfer suppose 10,000 rupees, or rather 1,000 rupees. So instead, because of this XORing, suppose he essentially finds out that 10,000 rupees is being transferred. Okay. So you see that there is, although it gives you a perfect security, but you have a problem of message integrity. So that is actually questionable. So therefore we require some other mechanisms, some other cryptographic primitives to solve these kind of scenarios, right? But so we will see this problem in our gradually as the class progresses. We will see some things which are called hash functions, and try to see how these problem can be circumvented. Okay. But at this point, let us try to think about this problem, that is, why not distribute the message the same way as the pad. So therefore the idea is that how do I make a cipher in which my size of the key is smaller than the size of the ciphertext, and still we are able to protect against a reasonable amount of a reasonably powerful adversary. So reasonable means in today's context. Okay. So maybe what we use as a thumb rule is that in today's world somebody can anything which is beyond 2 power 80 is considered to be hard. Okay. So if we can actually prove that an adversary will require 2 power of 80 trials, then actually it is considered to be quite hard. Okay. So you know that powers of 2 increases very fast, right? So anything which is say 2 power of 40, less than 2 power of 40 is considered to be quite easy, but beyond 2 power of 40 and beyond is actually reasonably hard, and beyond 2 power 80 is actually considered to be impossible even in today's world. Okay. So that is the idea of computational security. Okay. So I have already defined, or rather told you, what is meant by entropy. Okay. So what is entropy? The entropy was essentially a measure, it was basically a mathematical measure of uncertainty or information, right? So therefore consider that there is a probability distribution of outcomes of an experiment. Suppose you have a coin and you are tossing that coin. Okay. So head can occur or tail can occur. So what is the probability of head or tail? It's in general half, right? If it is not like the coin that was used in where. So in other cases actually it's a probability of occurrence of head or tail is in general half, right? So therefore, so if you consider or observe say n number of experiments, okay, and do an n plus 1th toss, what is the probability of occurrence? I mean what is the outcome that you would expect? If it is an unbiased coin, you still do not have any clue, right? Which means your uncertainty, in order to represent your uncertainty, you still require 1 bit, because you still require to denote a 0 or a 1 depending upon the outcome, right? So that you do not know that. Okay. And similarly the same thing, so that is uncertainty. Okay. The same thing if you talk in terms of information, it means that let us do the n plus 1th toss and let us report the outcome. So in order to report that, I also require a 1 bit information. So you see that information and uncertainty are somewhere related. Okay. And in order to mathematically quantize that, we use the term entropy. Okay. So I have already told you what is entropy, right? Entropy is nothing but the, so if you have got some number of symbols, you multiply the probability of the symbol with the corresponding logarithm of that probability. Okay. And that you keep on adding, right? So that is how you obtain the corresponding value of the entropy. So let us consider a scenario where your P or plain text is made of A and B, and therefore the occurrence of your A as a probability, the probability of occurrence of A is say 1 by 4, and the probability of occurrence of B is 3 by 4. And your K is say K1, K2 and K3. Okay. So what is the probability that K1 occurs is half, K2 occurs and K3 occurs is 1 by 4. Okay. So now what is the value of HP? That is, what is the value of entropy of P? So what we can do is that we can just multiply 1 by 4 with the corresponding logarithm, that is 1 by 4. Okay. And so you can either do a multiplication with log of 1 by px, or you can multiply this and keep a negative term ahead. Okay. So if you do that and if you add such type of things, such type of all the terms, then finally you get 0.81. What is the unit of this? It is bits. Okay. So similarly for HK, I mean you can do a similar kind of calculation, it will come down to 1.5 bits. Okay. In the case of HC, it will come to 1.85 bits. So this you can check. Okay. These slides are available, you can check. So what is the idea? The idea is that essentially what you are trying to capture is that in order to know the plain text, how many bits are required. Okay. In order to know the K, how many bits are required, how many key bits of information are there in the cipher text. Okay. So another point to be noted out here, and another remark could be that when you are multiplying the xi with the corresponding logarithm, right, so what you are multiplying is the probability of xi with the probability of the logarithm of that, right, with the logarithm of the probability. So it may happen that your probability works to 0, rather, so suppose some probability is 0. So in that case, what is the value of log of 0? So this becomes undefined term, right? But then you know that there is a limiting condition which says that when limit x tends to 0, then this particular value tends to 0. So you know that there is a, we can actually show that, right, using the theory of limits, right. So therefore this is actually quite reasonable to use this. So if there is a symbol for which the probability is actually 0, then this term computes to will go to 0. Okay. So therefore this is quite a well defined formula. Okay. You see that? So therefore, anyway, coming back to our simple calculation, we can just employ our simple formula and compute the corresponding entropies. Okay. So we will see a particular case which is called Huffman encoding. I think we know, many of us know that, but let us consider in terms of entropy. So therefore, Huffman encoding essentially is an encoding style which tries to encode symbols and tries to ensure that minimum amount of information is, or rather minimum number of bits is required. Okay. So it is commonly used for compression. Okay. So therefore, consider S, which is a discrete source of symbols making S1 to Sk. So the question is, can we encode these messages such that their average length is as short as possible. Okay. So if you would have computed the value of Hs, then that was the minimum number of bits required to encode, or rather to convey this information which the source conveys, right. So therefore, given these messages, can we encode them in such a fashion, so that is a limit, right. So therefore, Hs gives you a limiting condition, how many bits are required to represent the source symbols. Okay. So can we devise an encoding principle which goes close to the limiting condition. Okay. So that, in order to achieve that, Huffman coding essentially gives you an optimal solution, right. So Huffman coding gives you an optimal solution in order to achieve this. Okay. So let us see how Huffman encoding works. The idea is as follows: the message set X has got a probability distribution. So suppose you have got symbols like X1 to Xj, and what you can do is you can just arrange them in an ascending order. Okay. So what you do is that initially the codes of each elements are empty. So initially you have not coded them with anything. Then what you do is that you choose two elements among all these elements which has got the minimum probability. Okay. And then you denote one of them by 0 and the other one by 1. Okay. And then what you do is that you merge them into a new letter. Okay. So you merge them into a new letter, which means that, suppose consider X1 and X2 which has got the minimum probabilities. Okay. So what you would do is that you will make a letter into a new letter, that is X12, and with the probability as the sum of X1 and X2. Okay. So encode the smaller letter as 0 and the larger one as, say, 1. Okay. So which means that X1 is being encoded by 0 and this one by 1, and then what you have done is that you have merged them into a single letter, say X12, and the probability of X12 is the sum of probability of X1 and X2. Okay. So when only one element remains, then the code of each letter can be constructed by reading the sequence backwards. Okay. So therefore, you continue to doing that, and after that you start tracing from the back. Okay. And then you obtain the encodings of each possible letters. Okay. So if this informal description is not clear to us, I guess let us consider an example, okay, to make it more clear. So therefore, consider like A, B, C, D and E makes X, and probability of A is 0.05, probability of B is 0.10, probability of C is 0.12, D is 0.13 and E is 0.6. Okay. So in this case, consider how do I do an Huffman coding. So consider, for example, A and B. So what is the probability of A? It is 0.05 and of B is 0.10. So you see that which are the two minimum probabilities? It is 0.05 and 0.10. So what you do is that you encode them with 0 and you encode this with 1, and if you consider the combination of, or rather both these symbols, then the probability of this symbol together would be sum of 0.05 plus 0.10. So that is 0.15. Okay. So then the next two minimum frequency or minimum probabilities will be that of C and D, right, because the probability of C is what, 0.12 and the probability of D is 0.13. Okay. So you again do the similar thing, you encode this with 0 and 1, and the summation you consider and make it 0.25. Okay. Right. So what is the probability of what is the next two minimum occurring probabilities now? It is 0.15 and 0.25. Okay. So what you do is that you make it 0 and you denote this by 1, and the summation would be 0.4. Okay. So now consider 0.4 and 0.6. Okay, and you encode this with 0 and this with 1. Okay, this 1 should have been down here, and if you sum them, it becomes equal to 1. Okay. So now if I would like to construct the encoding of A, I will start doing it from the back. Okay. So the encoding of A will be 1 okay, will be 0 followed by 0 followed by 0. Similarly, you can obtain the encodings of the others as well. Okay. So this is how the encoding works. A is 3 zeros, B is 0 0 1. You can see that B is 0 0 and 1. Okay. C is 0 1 followed by 0, and D is 0 1 followed by 1, and E is denoted by 1 itself. Okay. So you see that for E I have used only one bit. Why? Because that is the most frequently occurring letter. So if you see the frequencies, E is the most frequently occurring letters, right? So the idea behind Huffman coding is that since E will occur most of the time, I will use as minimum bits as possible for that. Okay, and that is the way how I save bits, how I do compression. That's why Huffman encoding is used for compression, right? So this is a very simple technique, right? So given any sort of any letters, you can do Huffman encoding, right? And you can engage that to do a compression also, right? So you see that this essentially conveys nicely the meaning of information, right? So this is a practical example of where information theory can be applied. It can be applied to do compression. There are several examples like that. So some more results on entropy, although I will not be proving them, but you can actually find the proof in Stinson's book. Okay, it uses something which is called Jensen's inequality, but I guess we can just see from using our intuition. We should be able to find, I mean, rather understand a lot of it, but just by using the idea that entropy conveys nothing but information. Okay, so consider that x and y are two random variables, and consider a joint distribution of x and y. All of us know what is a joint probability distribution, right? So it means that x and y are both essentially varying. Instead of only one x varying or y varying, both of them are varying, and we are observing the probability distribution, right? So that means given x comma y, there is a probability distribution for x comma y. It is p x comma y. Okay, it could be xi comma yj, and I am considered with the probability distributions like that. Okay. So you see that h of x comma y means essentially is lesser than equal to hx plus hy. Okay. So we can actually we should be able to understand this. Why? Now because I mean for any case we would have said that okay, hx comma y, that is the information which is there in, I mean sort of the distribution of x comma y is the same as that of hx, that is the information of x plus the information of y given x. Okay. So actually we could have converted this and represented this in the form of an equality. Okay. So consider this line, for example, hx comma y is equal to hy plus hx given y. So you see this is the information of x comma y is the same as the information of y plus the information of x given the information of y. Right? Do you understand that intuitively? All of you? Yes. So if x and y are two independent, I mean okay, I mean even otherwise hx given y, which means what? That means some amount of information is given to you about y. Okay. So this information, that is hx given y, should be less than or equal to hx, right? Because y is giving you some information, right? So that means if you combine this, then you obtain this, that is hx comma y is actually less than equal to hx plus hy. Do you see that? Because of the fact that hx comma y is actually less than equal to hx, right? So therefore you know that hx comma y is actually less than equal to hxx plus hy given x, that is equal. So we have the equality in that case, and hy given x is actually lesser than equal to hy. So therefore you obtain this inequality. All of us see that? Yes. So therefore when x and y are independent, then actually we can write that h of x given y is equal to h of x, because y doesn't give you any information, right? So in that case we have the equality that hx comma y is equal to hx plus hy, right? So which means that this is actually true when x and y are two independent events. Okay. So this is a way how you can actually compute the conditional probability. So it says that h of x given y you can compute in this fashion. Okay. So So actually I can try to use this to find out. Right? Do you understand why this works? Because in the first case what we have done is that we have just considered, so there are two random variables, right, x and y. So in the first sigma we have varied y for all, we have taken the value that this random variable y takes a value say small y, okay, and we are computing this equation, okay, this sigma. So after that we are also varying the value of, we are also assuming that this random variable x takes a value small x, okay. So there are two sigmas in that case, okay, and that essentially leads to these corresponding equations, okay. So in order to compute hx given y, since there are two random variables, we will be require two operations of the sigma, okay. So do you see that? So it is just you take one you vary one of them and then vary the other random variable, okay. So you can obtain the, you can essentially compute this given the probability distribution of, given the conditional probability that px given y. So in that case, given for all possible values of x and y, if that is given, then you can compute the corresponding value of hx given y, okay. So today we will actually try to prove this theorem. It says that if there is an encryption system, say P, C, K, D, E, so we have seen that there is a 5-tuple encryption system, then we have got this theorem which says that h of k given C is equal to h of k plus h of p minus h of c, okay. This is actually called the equivocation of key also, okay. So equivocation of the key given the ciphertext. So what does equivocation of key mean? So that is something which is called the ambiguity, okay, something related to the ambiguity. Why? Now because the ciphertext C is leaked to you, is given to you. So the question is, what is the amount of uncertainty that still remains of the key, okay. So you see that h of k given C means what? H of k means what? It is the uncertainty of the key. So h of k given C means what is the uncertainty of k given the value of the ciphertext, okay, and that actually can be proved to be equal to hk plus hp minus hc, okay. So you see that the proof, so we will try to prove. So the first line says that h of p comma k is equal to h of c comma k. Can you say why? Can you think of why? So how can you obtain h p comma k comma c? Is this correct? So what is the value of this h of c comma h of c given p comma k? So given p, that is the plain text, and given the k, what is the uncertainty remaining of the ciphertext? 0. So therefore this is equal to h of p comma k. So similarly you could have done like h of c comma k plus h of p given c comma k. So this was also equal to 0. So therefore this computes to 0, this also computes to 0. So what you have in the output is h of c comma k. So therefore you see that both of them are equal, right. So therefore h of p comma k and h of c comma k are equal. You see that? So therefore we can say that h of p comma k is equal to h of c comma k, right. Is this clear? Right. So therefore h of p comma k, now we can denote them by h of p plus h of k. Why? Why can I write that h of p comma k is equal to, yeah, because both of them are independent. So we can write that h of p comma k is equal to h of p plus k because p and k are independent. Okay. But what about h of c comma k? It is equal to h of c plus h of k given c, because k and c are not independent. So we cannot write like before, right? So therefore, so again I write here that since k and c are not independent, right? So therefore now you can use or combine these two equations, okay, and what you can obtain is h of p plus h of k is equal to h of c plus h of k given c, and that implies that h of k given c is equal to h of p plus h of k minus h of c, right? So that is called, so therefore we know that given the entropy of the plain text, entropy of the k and entropy of the cipher text, how to ascertain the value of, or rather the ambiguity of k given the value of cipher text, right? So the next question that I would like to ask you, that we have also told that this is an equivocation of the key. So why it is called equivocation? So do you have any idea about why it's called equivocation? So it is something to related with the way I told that how cryptanalysis works. Okay, so therefore given the value of the cipher text, what we do is that we choose or rather guess the value of the key and then go back and obtain the plain text, right? So that plain text can be meaningful plain text, maybe meaningless plain text also, right? But what we are basically believing is that if the value of the k or the key is the correct key, then the plain text would be meaningful. But actually speaking, there could be some situations, okay, where even if the key that you guess, okay, is actually wrong, even then the plain text makes sense. Okay, so these type of keys are called spurious keys. Okay, so therefore that means given the cipher text, there are some keys which are not the actual key, and those keys are known as the spurious keys. Okay, so you see that we are slowly trying to sort of formally or mathematically state or rather describe what is meant by cryptanalysis. Okay, what is the meant by the idea of cryptanalysis. Okay, so but this one, that is this hk given c, or the ambiguity of the k given the ciphertext c, is actually very important. Okay, so imagine that if this hk given c is equal to hk, right? So what does it mean? It means that a ciphertext does not leak any information of the k, right? And that when that happens, we say that we have got something which is called ideal security. Okay, so it says that such type of ciphers are called ideal ciphers. So you see that hk given c, when it becomes equal to hk, it means that the uncertainty of the key given the cryptogram is the same as that of the key without the cryptogram. Okay, and this definition was given by Shannon in his paper. Okay, and it says that this is called ideal security. Okay, so what does it mean? That is, in case of perfect security, we had a different notion, right? But this is actually a deviation from the perfect security. But what we are saying is that we have got ideal security. Okay, such kind of ciphers are called ideal ciphers. For perfect securities, we had that hp is equal to hp given c, but for, or equivalently hc equal to hc given p. But for ideal security, we have got hk given c is equal to hk. Okay, and when that happens, what does it mean? It means that if you cancel hk given c and if you cancel hk, then you have got hp minus hc working to 0. So that means the hp and hc's both the entropies should be equal, right. That is, the ciphertext will have the same entropy as that of the plain text, right. So therefore now consider a simple shift cipher. The English language had a frequency distribution and hence an entropy, right. So imagine that a ciphertext also possesses the same entropy, then HP and HC would have been identical, right, and therefore we would have obtained HK given C is equal to HK, right, and that is the definition of ideal ciphers. Okay. So we know what is, so therefore at this point all of us know what is meant by perfect secured ciphers, we know what is meant by ideal secured cipher, and we know how to prove that given a crypto system whether it is perfectly secured or whether it is ideally secured. Okay. So we would be able to compute these entropies, and accordingly we will be able to compute the values of these equalities, whether they match or whether they do not match. Okay. So going ahead, for perfect ciphers the key size is infinite if the message size is infinite, right. So however, if a shorter key size is used, then the cipher can be attacked by someone who has got an infinite computational power, like DES, as I told you, having 56-bit key, right, it is much lesser than its plain text, right, because the plain text size is even much larger, right. So therefore one key is being used for so many encryptions. Okay. So your key size is larger, and therefore you can actually, if there is an infinitely powerful adversary, then he can break the crypto system. Okay. So the idea is that HK given C gives us this idea of security or insecurity. It says that given this ciphertext, what is the amount of information that is still required to know the value of the key. Okay. So therefore now we will slowly try to go into something which is more practical. So what we have said to you is that in case of a DES, for example, right, so in case of a DES what we have defined is that if for a given plain text, if you use a value of key, and each time if you choose a value of key at random, then you still obtain a perfectly secured cipher. Do you see that? Like a DES has got, I would like to say that a DES has got, so it's a 56-bit message, for example, okay, and you consider a cipher like this. So maybe the name is DES, it's not so important at this point, and the key is also 56 bits. Okay. So which means that for this plain text you are transforming that and obtaining the value of the ciphertext, right. So you obtain the value of the corresponding ciphertext. So imagine the ciphertext is also, the size is still 56 bits. Okay. So now tell me that if the size, that for each plain text if you choose a key at random, right, then you would still have obtained a perfectly secured cipher. But instead what you do is that for a session, like for example if you say that in a session you say transfer say P1, P2 and say maybe PL such plain texts, okay, and all of them you encrypt by a single key. So therefore there is some master key K, and you use all of them to encrypt, you encode all of them and you make ciphertext like C1, C2 to CL. Okay. So all of them have been encrypted by key K. All of the plain texts have been encrypted by key K, right. So now that means that we are not actually doing what is to be done in a perfectly secured cipher. Okay. Therefore an unbounded adversary can break this system, right. So the next question that we will consider is that how many such encryptions can we do so that an unbounded adversary cannot break it. Okay. So that means what is the minimum number of such ciphertexts which should be encrypted, okay, which can, rather what is the maximum number of ciphertext which can be, or maximum number of plain text which can be encrypted by the same ciphertext, by the same key, which cannot be broken by an unbounded adversary. Okay. Or posing the problem in another way, to an unbounded adversary, how many ciphertexts at maximum shall I provide which has been encrypted by the same key so that he cannot still break the system, right. And this is actually known as the unicity distance. Okay. So we will actually try to see what is unicity distance in the next day's class, but in today's class I am trying to pose the problem. Okay. So what I am trying to conclude from here is that even for DES, AES, although I am saying that it is not perfectly secured and hence can be broken to by an unbounded adversary, what I am trying to say is that if you use it within its unicity distance, then even an unbounded adversary cannot break it. Okay. So actually we can prove that we can show that the unicity distance of DES is 2. Okay, which means that if you use two plain text, if you encrypt two plain text by the same key using the DES function, then even an unbounded adversary cannot break it. Okay. So you see it's quite interesting, right. So we will try to prove this result in the class. So this is the question. So the question is that how do you protect the data against a brute force attacker with infinite computational power? Okay. So what Shannon defined is that Shannon in his classical paper, seminal paper, defined something which is called unicity distance, which we will call unicity in short, as the least amount of plain text which can be deciphered uniquely from the corresponding cipher text given unbounded resources by the attacker. Okay. So the idea is as follows, that is what I am trying to say to you is that consider a simple shift cipher. Okay. So consider all say 3 gram letters. 3 gram letters means trigram letters. Say THE, like this kind of things. Okay. So what you do is that you try to guess the value of the key and you try to obtain such kind of trigrams. Okay. So suppose if your key is correct, then that trigram would have made sense, right? Would have been a meaningful trigram. So immediately you would have maybe stored that okay, this is a possible guess of the key. Okay. But in reality actually you do not get one such possible key, you get some other keys also. So these are called spurious keys. Okay. And the moment you are able to uniquely identify the key means what? Your spurious key set is essentially 0, is a null set, which means that there is a unique value of the key which will be which you should be able to compute, which you should be able to deduce, right. So what you do in our simple case of trigram experiment, you take another trigram and take the same key and you decrypt back and you see that okay, whether this makes sense or not, and this way you can prune the possible spurious keys, right. So the question is, how many such trigrams would you require to uniquely find out a key? The moment you do that, you have uniquely deduced the key, right. So that number of trigrams that you require is called the unicity distance of a simple substitution cipher in this case. Okay. And this way actually for any cipher we should be able to try to give you a margin of the corresponding unicity distance. Okay. And that is exactly what we will do in our next test class. Okay. So an important point is that a common misconception is that any cipher can be attacked by exhaustively trying all possible keys. Okay. So thus DES, which has a 56-bit key, can also be broken by brute force, but if the cipher is used within its unicity distance, then even DES is theoretically secured like the one-time pad. Okay. So if you use any cipher, if you compute its unicity distance and if you use the cipher within its unicity distance, then essentially you obtain security against an unbounded adversary. Okay. But the thing is that we have to know how to compute the unicity distance, right. So that is something which you have to compute. Okay. So therefore this is what I have already told you, it is an idea of a spurious key. The spurious key idea is as follows, that as I told you that HK given C is the amount of uncertainty that remains of the key after the cipher text is revealed. Okay. So therefore after the cipher text is revealed to you as the cipher text C, what is the amount of uncertainty that you have about the key? We know that this is called the key equivocation. So there are some keys which seem to be equivalent, something or other which tries to speak the same thing. Okay. So attacker, what it does is that to guess the key from the cipher text, shall guess the key and decrypt the corresponding cipher. Okay. He checks whether the plain text obtained is meaningful English or not. If not, then he rules out the key. Okay. But due to redundancy of language, more than one key will actually pass this test. Okay. And those keys apart from the correct key are known as the spurious keys. So the idea is that the attacker will try to make the spurious key set null, right. He will try to reduce the number of spurious keys and try to conclude at one single unique key. A number of attempts or number of cipher text that he will require for this is called unicity distance, right. so I will gradually proceed with this, but I mean, in order to just define what I am trying to say is that I will try to show to you that actually you can compute the value of redundancy using a simple formula. Okay, that is RL redundancy is equal to 1 minus HL by log p base 2. Okay, so what I will try to sort of gradually show to you what is meant by redundancy, and from there we will try to find out how to compute the spurious set key and obtain the value of the unicity distance. Okay, but that we will do in the next day's class. Okay, so any questions till this point? So if not, then please go back and solve an exercise. I give you an assignment which you can just note down. It says that let n be a positive integer, a Latin square of order n is an n cross n array L with integers 1, 2, so on till n, such that every integer occurs exactly once in each row and column. An example for n equal to 3 as follows. Okay, so therefore this is a simple example for n equal to 1, 2 and 3. It shows you how essentially a Latin square works. Okay, so what you have to prove in our class is that, or rather you can take this as an assignment, is that you have to prove that this is actually a perfectly secure cipher. Okay, so therefore again I repeat the question. It says the Latin square of order n is an n cross n array L with integers 1 to n such that every integer occurs exactly once in each row. So you see that 1, 2, 3 occurs exactly once, so in each of the rows. Okay, so therefore this gives you an example of how an encryption works, right? And therefore what you have to prove is that given any Latin square of order n, we can define a related crypto system as follows. It says that Eij, okay, so you can denote the I by the key and j as this thing, and what you have to do is that you have to compute the corresponding value of the corresponding cipher text, and you have to prove from the computation of probabilities that the so you should not use the straightforward equations. Okay, so you have to actually do by computing each of the individual probabilities and prove that a Latin square crypto system achieves perfect secrecy. Okay, and you have to give it on 2809, so that's not 08. So please submit handwritten proofs, because don't submit soft copies. Okay, just give handwritten proofs, write handwritten proofs and submit it within the deadline. Okay.